So, homework 2 was technically due Friday. I know we're still in the grace period. Most people still haven't turned it in yet, but same announcement the last 3 classes. If you're having trouble, please shoot me an email. I'll help you with the R. Don't drive yourself crazy over it, because I'm also hopefully going to post homework 3 tonight, and hoping to avoid people getting too far behind. Anyway. So today, as we see, we'll be discussing hypothesis tests for categorical data. It's kind of a generalization of what we considered last Friday. Last Friday we considered the special case of proportions. Now we'll consider categorical data more generally and what types of inferences you can make on categorical data. So, some examples of categorical data analysis. A simple case would be like a case that we considered on Friday, where, say, you give people either an active drug or a placebo, and you also have a dichotomous outcome, either no pain relief or pain relief. You want to test the null hypothesis of no association between these two variables, that is, that the active drug isn't more likely to produce pain relief than the placebo. And for a simple case like that, you can use the proportion test methodology that I described on Friday, but you can envision cases we might want to do something more complicated than that. Let's say that you have two different drugs that you want to compare to one another, so drug 1, drug 2, and placebo. And let's also say that you have an outcome with 3 possible levels rather than 2 possible levels, that say your outcomes can be no pain relief whatsoever, some pain relief, or complete pain relief. And you want to test the null hypothesis of no association between these two types of drugs plus placebo and these 3 different outcomes. In that case, it's no longer a simple case of proportions. We need some more complicated methodology. And you also may want to do some hypothesis tests about categorical data when there isn't an obvious outcome variable or something like that. If you ever do genetics experiments, for instance, you may want to say, well, are the allele frequencies that we observe in this data set consistent with Hardy-Weinberg equilibrium? In a lot of genetic studies, the theory is that if your data is out of Hardy-Weinberg equilibrium, then that indicates there's probably some type of problem with your data. So this is an important question in a lot of modern genetic studies. And in that case, you have counts of several different genotypes, and you want to test the null hypothesis these counts are equal to some expected counts, but there isn't necessarily some outcome variables. Today I'll describe how you can do that type of test as well. Oh, far and away the most common method for doing this type of analysis is what's called the chi-square test. Later on today we'll discuss a couple alternatives to chi-square tests, but this is still the one that gets used about 90-95% of the time. And there are several variations of chi-square tests that we'll consider, but the simplest one is, say that you have a random sample of n different categorical observations, and let's say that you have some hypothesized proportion of the observations that should be in one of each of several possible categories. And you can use a chi-square test to test this type of hypothesis, so I'll illustrate here in a second. So here's a simple genetics example that I pulled out of a textbook somewhere, that there's a type of Snapdragon that can have either red, pink, or white flowers, and under a certain type of genetic model, I believe this is just a codominant model, if you have pink-colored flowers, that should produce progeny that are red, pink, and white with the proportion 1 to 2 to 1. In other words, about half of the progeny should be pink, but 25% should be red and 25% should be white. As I said, I think this is just a codominant model that if you have 2 copies of this specific allele, the flower is red. If you have 1, it's pink. If you have 0, then it's white. So if you self-pollinate a bunch of pink flowers, where all of them should have exactly 1 allele, then you would expect 25% to have 2 of these alleles and be red, 50% to have 1 and be pink, and 25% to have 1 and be white. But for the purpose of this class, that's not as important. The important part is that under our null hypothesis H0, we hypothesize the probability of a red flower is 0.25, the probability of a pink flower is 0.5, and the probability of a white flower is 0.25. We can use chi-square tests to test the null hypothesis that the observed frequencies are consistent with these hypothesized frequencies, as I'll describe here in a minute. So let's say that we do an experiment, we get 54 red flowers, 122 pink flowers, and there's a typo on the slide that needs to be fixed, and 58 white flowers. And we want to see if our data is consistent with this particular null hypothesis. So the first step to performing this type of chi-square test is to compute the expected frequencies under the null hypothesis. Under H0, if we plant 234 flowers, we would expect to observe 234 times 0.25, in other words 58.5 red flowers, 234 times 0.5 or 117 pink flowers, and likewise 58.5 white flowers. So the purpose of the chi-square test say, do the numbers that we observe that I gave on the previous slide differ significantly from these expected frequencies? Flip the slide in the wrong direction. So we're given, so to perform this test you can do a chi-square test, which is that if you're given n frequencies that we call OI and then expected frequencies EI, then to calculate the chi-square test, for each observed frequency, subtract the expected frequency, square it, divide by the expected, and do this separately for each categories, and then add them all up. And if you do some math that I won't show you, you can show that this particular test statistic should have a chi-square distribution with n-1 degrees of freedom. For those who are interested, a chi-square distribution is just the square of a normal distribution. And so if you square n-1 normal random variables and add them together, that will have a chi-square distribution with n-1 degrees of freedom. But for this class, you don't need to know about that. You can just use R to get these numbers. But important thing, it's just like we did with t-tests and z-tests and so on. We know what distribution this test statistic should have under the assumption the null hypothesis is true. So we can calculate this test statistic to see if the observed data are consistent with our hypothesized data. And note that the degrees of freedom is n-1, 1 less than the number of categories. So, to calculate the chi-square statistic, the chi-square test statistic on the Snapdragon data, recall that we observed 54 red flowers, 122 pink flowers, and 58 white flowers. The chi-square test statistic is always observed minus expected squared divided by expected, so 54 minus 58.5 squared divided by 58.5. 122 minus 117 squared divided by 117 plus 58 minus 58.5 squared divided by 58.5. Easy enough, hopefully. And So, as before, there's a number of ways that you can do this test in R. The most complicated way, which in practice you probably won't need to do very often, if ever, is to just actually calculate the test statistic by hand and use this function p chi-squared. So do the same statistic that we had on the previous slide. Observed minus expected squared divided by expected plus observed minus expected squared divided by expected. That should have a chi-square distribution with 2 degrees of freedom, because there's 3 different categories. The degrees of freedom is always 1 less than the number of categories. So 2 degrees of freedom. And then when you calculate a chi-square test statistic manually in R, you'll always go 1 minus p chi-squared. Because in R, whenever you use p chi-squared, p norm, pt, any other function like that, it always gives you the probability of getting a number less than what you observe. And with the chi-square statistic, you want to reject for large values of the test statistic, so you want the probability of getting a test statistic as large or larger than what you observed. So it'll always be 1 minus this value. In this case, we get a p-value of 0.754, so we definitely fail to reject the null hypothesis here, and it's probably okay to assume that the data is in fact, the hypothesized genetic model is in fact correct. So, in general, p chi-squared of x, degrees of freedom, that will give you the probability that a chi-square distribution with specified number of degrees of freedom is less than a given value x. As I mentioned on the earlier slide, in practice, when you're doing these tests, pretty much every time you will want the upper tail of a chi-square distribution, the probability of observing something larger than your test statistic, so you'll want 1 minus this p chi-square value. But an easier way to do this chi-square test is using this function chi-square.test in R. In this case, you give it 3 arguments. The first 3 arguments, well, not necessarily 3 arguments. You give it 2 sets of vectors. The first is a vector of counts. The second is a vector of hypothesized probabilities. So in this case, our counts are 54, 122, and 58. Our hypothesized probabilities are 0.25, 0.5, and 0.25. So, and you can see we end up with the same p-value that we got on the previous slide, about 0.754, and this syntax is easier than having to manually calculate the test statistic and use p chi-squared and run the risk of entering your data in wrong and all that stuff. So, recommend for practical purposes you use this syntax because it's easier. And in general, this chi-square.test command will perform a test the null hypothesis that your observed frequencies in a given vector match the expected proportions. And this command is fairly versatile as well. You can do it for some other types of chi-square tests, as I'll discuss here in a minute. So, let's go back to the clinical trial example that we discussed on Friday. Recall that in this particular clinical trial, people either got an active drug or a placebo, and some patients experienced pain relief and some patients didn't. There were 75 out of 125 who experienced pain relief under the active drug versus 52 out of 122 who got the placebo. And last week we discussed how you could test the null hypothesis of no association between the treatment and pain relief using proportion tests. Today, we'll revisit this example and show how you can do it using chi-squared tests. So, the basic idea is the same as the chi-square test that we discussed previously, that basically you just, for each cell, you just kind of go observe minus expected squared divided by expected, plus observe minus expected squared divided by expected. Question is, so how do you calculate the expected cell counts in this case? Well, under the null hypothesis in this case, whether you got the active drug or the placebo should be independent of whether or not you experience pain relief. So, to get these expected cell counts, you can assume that treatment, placebo versus active drug and pain relief, no pain relief versus pain relief should be independent of one another. So you can calculate these expected cell counts under this assumption of independence. So we'll just create a little 2x2 table here. There are 75 who in the treatment group who had pain relief, 50 in the treatment group who didn't have pain relief. In the placebo group, there were 52 with pain relief, 70 without pain relief. So if we assume that these two categories are independent of one another, then a total of 127 out of 247 people experienced pain relief. In other words, 51.4 of the people experienced pain relief. So among patients in the treatment group, we would expect 125 total patients in the treatment group, 51.4 of them to experience pain relief. So 125 times 0.514, we would expect about 64.27 patients with pain relief, and 125 times 0.486 patients to not experience pain relief. So, in general, if you work out the math, what that means is to get the expected count in any particular cell, you can take the row sum of that particular, or the column sum for the particular column. Say we want to find the expected number of people who experience pain relief in the treatment group. You can take the column sum, which is 127, the row sum, which is 125, multiply those two together, and then divide by the total. If you do that, you get 64.27. In this category, in no pain relief, you get 125 times 120 divided by 247, which turns out to be about 60.73, and then repeat this for each possible category. Yeah, I guess basically just said this in general, the expected cell count is just going to be row total times column total divided by overall total. So treatment, pain relief, you would expect row total 125 times column total 127 divided by overall total 247. Expected proportion experienced pain relief in the placebo group would be row total 122 times column total 127 divided by overall total 247, and so on in each possible cell. In practice, once again, R will do this for you. You don't have to bore yourself too much with the details, but it's useful to know how this is done just in case you ever need to do it by hand. And to calculate a chi-square test for a contingency table, it's if you're given observed cell counts, OI, and expected cell counts, EI, the chi-square test statistic is just like it was in the simpler case. You just go observed minus expected squared divided by expected, and add that up over each of the cells in the table. The only thing that's not intuitive here is the degrees of freedom. The degrees of freedom is equal to the number r minus 1 times c minus 1, where r is the number of rows and c is the number of columns. This whole idea of degrees of freedom is highly confusing. When I try to explain it, half the time I end up messing it up myself. Basically, for the purpose of this class, I'm only going to ask you to do this in some simple cases. If you just remember these formulas, you should be fine. It has something to do with the idea that how many different variables can vary freely in a given table. And this, when we just looked at one variable at a time and proportions, like in the Snapdragon example, if you know that the first proportion is 0.25 and the second proportion is 0.5, then the final proportion has to be 0.25, so there's only two proportions that can vary freely. If you know the first two, then you know the third one, so there's only 2 degrees of freedom. In a 2 by 2 table, for each row and each column, if you know all the values but one in a row or all the values but one in a column, then you can calculate the last row or last column, so hence it's minus 1 in each case or something like that. Like I said, just use the formula or use R, and that way I won't have to confuse myself trying to explain it. But in this simple pain relief example, we have 2 rows and 2 columns. So the degrees of freedom is 2 minus 1 times 2 minus 1, or 1 times 1, which is equal to 1 degree of freedom. So if we want to calculate the chi-square test statistic for this clinical trial data below, you can use the observed and expected cell counts. The expected cell counts were calculated as I described a few slides back. And we also have the observed cell count. So to get the chi-square test statistic, we can just go 75 minus 64.3 squared divided by 64.3 plus 50 minus 60.7 divided by 60.7, etc., etc. Excuse me. So, if you wanted to do this in R and you want to make this painful by calculating the test statistic manually, this is how you would do it. First of all, I just calculate these expected counts using the formula I described earlier. 125 times 127 divided by 247, 125 times 120 divided by 247, blah, blah, blah. Then I go observed minus expected squared divided by expected plus observed minus expected squared divided by expected across all 4 cells of the all 4 cells of the table. As I described earlier, add 1 degree of freedom. Go 1 minus p chi-squared of all that, we get 0.006. Blah. Long and complicated, but it works, I suppose. As usual, there's an easier way to do it. In R, I think we may have messed with this a little bit in the past, but just to spell it out, what you can do is define a matrix in R that hopefully you've seen matrices before. It's just kind of an array of numbers where each row and each column contains a specific variable. So I tell R, let's create a matrix with 2 rows and 2 columns. Then I just fill in the matrix. Say the first row and the first column is 75. The first row and the second column is 50. Second row, first column is 52, etc., etc. I just fill in the counts from the table that I described earlier. If I type clin.trial to print out the data set that I just created, we see it's exactly the same table that I described earlier with the counts for this clinical trial data. So, to test the null hypothesis of no association between the rows and columns of this matrix, I go chi-square.test clin.trial, and we see we get a p-value pretty close to what I saw on the previous slide, but not exactly the same. If I do chi-square.test clin.trial correct equals false, then I get a p-value that's exactly the same as what I got on the previous slide. And if you look at the output here, you'll notice this one says Pearson's chi-square test with Yates continuity correction. This one just says Pearson's chi-square test. To be honest, I forget the difference between the two. I think the continuity correction has to do with the fact that when you use a chi-square test, that I really do not remember the details. You're using a chi-square test is also based on a normal approximation to your data. That, I mean, as I said, a chi-square distribution is just the square of a normal distribution. So this implicitly relies on the central limit theorem, such that observed minus expected squared divided by expected gives you a chi-square distribution, or a square of a normal. And a normal distribution is continuous, whereas count data is obviously categorical, and the continuity correction has something to do with the fact that when you try to do a normal, when you try to use a continuous approximation to categorical data, it's a little bit rough, and you can use this continuity correction to get slightly more accurate test statistics. That's honestly all I remember about this. If you asked me how this was calculated, I wouldn't have a clue. I'd have to go look it up. So, generally speaking, I think there's a general consensus that the test statistics and p-values you get using the continuity correction are a little bit closer to the objective truth. So I recommend that you use the continuity correction in this class and in future work. But if you ever need to reproduce the results without the continuity correction, that's the command to do it. And I mean, if for some reason you don't want to use the continuity correction in this class, I'm not going to be super uptight about this, because I mean, typically it doesn't make that much of a difference, as you can see here. So, in general, if you have a matrix X and you do chi-square.test of X, it'll test the null hypothesis that the rows and columns of the matrix are independent of one another. And if you ever need to reproduce the results of a chi-square test by hand, then you can do chi-square.test with correct equals false, as I noted earlier. By default, the parameter is correct equals true, and most of the time in practice you'll probably want to use correct equals true, because that gives you better results anyway, typically. And in general, in R, if you say matrix n row equals something, n columns equals something, that'll create a matrix. And looks like another typo in there. It should be capital R, referring to the program that we're using in this class, with a specified number of rows and columns. And if you want to reference the ith row and jth column of a matrix, just x brackets I comma j. If you've ever used other programming languages or other similar software packs, this is fairly standard notation, but if you haven't seen it before, that's how it's done. And another way of doing this chi-square.test command in R that may save you a little bit of typing is if you just tell our matrix number of rows, number of columns equal to whatever, by default it will create a matrix containing all missing values. You can also give R data to populate your matrix with when you use the matrix command. Here I say matrix 75, 52, 50, 70, and then n row equals 2. R is smart enough to realize, okay, if I have 4 numbers and it has to be packed into 2 rows, then it has to have 2 columns, so you don't have to tell it the number of columns. That will automatically create a matrix. Just like we saw in the previous slide, you see the p-value is identical to what we got earlier. That Doesn't really make a difference. It just saves you a little bit of typing. You don't have to fill in your matrix by hand. As I noted earlier, if you just say x equals matrix, n row equals 2, n column equals 2, that'll give you a 2 by 2 matrix where every element is missing, and our missing values are denoted by NA. Whereas if you say x equals matrix 1, 2, 3, 4, n rows equals 2, then it will create a matrix containing the values 1, 2, 3, and 4. And unless you tell it to do otherwise, when you tell R to populate a matrix, it will populate it by column. So it will give you 1, 2 in the first column, 3, 4 in the second column, which means you'll have 1, 3 on the first row and 2, 4 on the second row. For the purpose of doing chi-square tests, that doesn't matter at all. You can show very easily that if you take a chi-square test on a given matrix or the transpose of that matrix, you'll get the same results, but I'm mentioning that just as an FYI. When are you allowed to use chi-square tests? Well, as I mentioned earlier, chi-square tests are based on a normal approximation. Normal approximations can be problematic if your sample size is too small. For the chi-square test, generally speaking, the rule of thumb that all the books give is that if your expected cell counts are greater than 5, your chi-square test should be valid. I have searched high and low for like the original source of that rule of thumb, and I'm not sure that it exists. I find it fascinating that everybody says that, but if I ask somebody now, where's a reference that says it works if you have 5 and doesn't work if it's lower, nobody knows. And honestly, in my experience, even if your expected cell counts are less than 5, usually the chi-square test doesn't do too bad. But presumably, there are cases where it'll blow up if your expected cell counts are too low, given that every single textbook says this, and in fact, even in ours, I'll show you here in a second, if you try to compute a chi-square test when your expected cell counts are too small, it'll give you a warning. And there are some alternatives that you can use to the chi-square test when your expected cell counts are small that are probably worth using, that I'll describe here in a minute. So here's an example of where you could potentially get into trouble with chi-square tests. This is another example that I found in a book somewhere that basically, if you have a newborn baby that has a severe respiratory problem, you can use something called extracorporeal membrane oxygenation, which was a procedure that was believed could help babies survive when this happened more so than conventional medical therapy. So this was a study from somewhere where there were 29 babies treated with ECMO and 10 babies treated with conventional medical therapy. The expected count sizes were small because these respiratory conditions are not very common, so the sample size was somewhat limited. And with conventional medical therapy, you had about 6 babies that survived and 4 that died, whereas with ECMO, there was only 1 that died versus 28 that lived. So that looks like a pretty dramatic improvement, but it raised the question, is this statistically significant given our relatively modest sample size here? So let's see if we can perform a test to test the null hypothesis of no association between treatment and surviving the procedure. So let's say that I just mindlessly plug this into R using chi-square.test. the same syntax as before, 4, 6, 128 matrix with 2 rows, I get a p-value of about 0.015, which meets the usual threshold for significance. You'll notice I get a warning message here. This chi-square approximation may be incorrect, sign that maybe the p-value isn't quite right. What are some alternatives that one can use if you get this warning that the chi-squared approximation may be wrong? Well, one way to do it is to simulate your p-values. So I just do chi-square.test again, but I add this parameter simulate.p.value equals true. And basically, the way that the simulated p-values work is rather than using a normal approximation to compute your p-value in the chi-square test, basically the program just generates a bunch of random data with the same row and column counts in your matrix under the assumption that the null hypothesis is true. And then it just counts how many times when the null hypothesis is true, you get a test statistic more extreme than what you observe, and you divide that by the number of simulations to get your p-value. It's a little bit more complicated than that, but that's the basic idea. End up with a p-value of about 0.008 in this case, which again still meets the usual criteria for significance. The simulated p-values is closely related to the idea of bootstrapping that I'll start discussing on Wednesday. And in general, if you say chi-square.test x with the simulate.p.value equals true, tells R to do a simulated chi-square test. It will generate a bunch of random data, assuming the null hypothesis is true. See how many times this random data is more extreme than the observed data. Don't worry too much about the details for this class. R will do it for us automatically. The other alternative that you can use in this case is what's called Fisher's exact test, which, as the name implies, rather than using a normal approximation to calculate your p-value, it just computes the exact distribution of the data under the assumption that your null hypothesis is true and computes a p-value. In this case, we get 0.01, which I have to chuckle at the fact is almost identical to what we got with the chi-square test that supposedly produced invalid results. In my experience, this is fairly typical, that even when you get the warning that the chi-square approximation may be wrong, I find that when I use the exact procedures, it usually doesn't make that much of a difference. But just if you want to err on the side of safety, there are these alternatives. And as I said, Fisher's exact test computes an exact test for the null hypothesis. The rows and columns are independent. It's the same idea as the binom.test command that we discussed last week. The syntax is exactly the same as chi-square.test, that you just give it a matrix with rows and columns, with various rows and columns, with each cell representing the count of data points in that particular cell. It'll test the null hypothesis that the rows and columns are independent. So, now that I've given you 3 different alternatives for these types of problems, you may be wondering, so which one do I use? And I know this is a common frustration when people take elementary statistics classes, both this class and others, that people are wondering, okay, you've taught me all these different methods right now, how do I know which one to use in a particular case? And later on in this course, once we've been through a lot more stuff, I will try to give you some cheat sheets in terms of what type of approach do you use on what type of problem. But what we've discussed today is particularly tricky because there's 3 different methods for exactly the same problem, and it becomes the question is, so how do you know which one to use? So chi-square tests. And there isn't necessarily a right or wrong answer here, but just to briefly describe advantages and disadvantages of these approaches. A chi-square tests, the biggest advantage is they're what everybody uses. 90 to 95% of papers, as I said, if you look at their statistical methodology when they have to do this problem, they will use the chi-square test. And it's very easy to understand and explain, and the vast majority of the time it works fine. So, I mean, if you just use nothing but chi-square tests for the rest of your life, you're unlikely to get into much trouble. The biggest disadvantage to chi-square tests, I said, in principle, you can get into trouble if your expected cell counts are small. In my experience, you usually don't get into that much trouble, but it is a possible issue. And even if your numbers are fine, you could get reviewers yelling at you about this. The simulated chi-square tests is that don't rely on this normal approximation. So no matter how messed up your data is, the simulated chi-square test statistics should be fine. The disadvantages is, I mean, it's much harder to explain how you did this if you're writing your method section or to your PI or collaborator or whatever. Almost nobody actually does this in practice. R, I think, is one of the few statistical packages that will even compute this, so it's not commonly used. You'll get p-values and confidence intervals that are only approximate, and since they're based on simulated data, they're not 100% reproducible unless you tell R to save a particular random seed or something. If you run it and then your lab mate runs it next week, they might get slightly different numbers, which if you value reproducible science, I mean, even though it shouldn't change drastically, that's somewhat disconcerting. And also, particularly for large matrices, this can be slow. I mean, in my experience with modern computers, you need a really big data set and do a lot of simulations before this takes more than a couple seconds. But in principle, this could take a while to compute. And Fisher's exact test is advantage. It'll get you an exact p-value. You don't have to rely on a normal approximation, and it'll work just fine even if your expected cell counts are small or whatever. And this test, at least in my experience, is becoming more popular nowadays. It's because this is another one of those things that for a long time nobody learned about because we didn't have the software to compute it, and it was a pain to compute by hand. Whereas chi-square tests were easy to compute by hand, but now most statistical software packages will compute Fisher's exact test. And particularly I found, like, in a lot of genetics papers nowadays, they will use Fisher's exact test just because if you're looking at potentially like thousands or millions of genetic markers, your chi-square test assumptions are likely to be wonky on some of them, and rather than look at a million different markers to make sure that all your assumptions are satisfied, you just use Fisher's exact test and don't worry about it. So particularly for the 2x2 case, nobody's going to look at you cross-eyed if you use this. In fact, you can make a case that it's better than the chi-square test in that case. The problem with Fisher's exact tests, I mean, you need a computer to compute it. There's no really good way to write out how it's computed. Even more so, I mean, for the 2x2 case you kind of can, but you get larger than 2x2 and it becomes really difficult to compute. In fact, you get a reasonably large matrix, and I mean, you'll blow up your computer if you even try to compute this. R is usually smart enough to just crash with an error rather than actually blowing up your computer if you try to do it for something too large. But it can blow up your computer if you let it. I've seen it happen. And fact, like a couple of years ago, I put a problem on the final where some people tried to use Fisher's exact test on a large matrix, and I got a bunch of panic emails about their computers melting down. I'll try to avoid doing that again this year, but this is a potential concern. So, I mean, my personal opinion, you can get away with the regular chi-square test in almost all circumstances, and that's probably going to get you the least blowback from reviewers in most cases. If R gives you a warning that your expected cell counts are too low, then you can try these other methods just as a sanity check to make sure you're getting the approximate the same answer. And particularly in the 2x2 case, you may want to just go with Fisher's exact test because that's becoming fairly commonly used nowadays. And the other two methods, I mean, to me, the most useful situation are like, number one, you write a paper and the reviewer says, you shouldn't be using chi-square tests in this case. Your expected counts are too small. So you say, okay, fine, here's Fisher's exact test, here's a simulated test, whatever. Get off my back. Or if you're like writing a grant proposal or something and you want to make sure reviewers won't yell at you for your method, you can say, well, we expect to have small counts, we'll use Fisher's exact test, something along those lines. But for this class, I'm not going to be super uptight about this. Just as I always say, both for this class and for real life, a lot of times there's not a single right or wrong answer. The most important thing is that you justify whatever decision that you make. If you can, on the homework or an exam, say, I use this test for this reason, and it's a defensible reason, we'll give you the points. It's generally speaking, unless something is just horribly, indefensibly wrong, we don't have a specific right answer in mind. We're just more concerned with your ability to defend the decisions you made. Oh, things to remember for today is that we can test hypotheses about categorical data using chi-square tests, and you can test hypotheses about proportions of a single categorical variable or test whether a couple categorical variables are independent, and if your expected cell counts are small, then you can consider some alternative methods. And here's a list of some R commands for today, simulated p-values, and also for Fisher's exact test and how to create matrices. Any questions about anything today?